Question is, does water conduct electricity? Does water conduct electricity? And so you may remember this device we had out earlier this semester. In fact, this was a day one type of demo that we did. And we'll see what you remember from day one. Hopefully you do better than the morning class did. And to make sure this thing works, and they don't sell stuff like this anymore. I mean, this is like truly an original. This is very highly dangerous because, of course, somebody could grab, get a shock or something, So you got to be careful here, and that's why I insulate it with a paper towel. And if the circuit is completed, then the light bulb goes on. 5, 4, 3, 2, 1. And we have 68% of you that say yes, and 32% say no. So apparently we did not make a very big impact on you the first day because it's not overwhelmingly one way or the other. But water does not conduct electricity. Water does not conduct electricity. So those of you that said yes, here's the second time now that you've seen that this semester. Water does not conduct electricity. And so what we're going to do today is we're going to run through and test a number of different substances. We're going to make a table. We're going to list the substance, and then we're going to give its formula, and then we're going to tell whether it is an electrolyte or non-electrolyte. And in this table, again, we're going to have 3 columns. And for the first substance, we looked at water. And now, here's your test. If you can't pass this test, you will not pass this class. What is the formula for water? H2O, and it's H with a little 2. And no, call that a subscript, H2O. And now, when we use the term electrolyte, non-electrolyte, here's what those terms mean. If we say that something is an electrolyte, what that means is that an electrolyte is a substance that conducts electricity when dissolved in water. Now, chemists actually use it a little more liberally. We might also talk about it if it's in its molten state or its liquid state. And in that sense, we could also say that water is a non-electrolyte because it does not conduct electricity in its liquid state. And if we put water into water, it still doesn't conduct electricity. Yes, Gabby?
So how come when they make smart water and stuff, they're like, oh, it has electrolytes? What is that like for taste?
Well, not going to quite answer that yet. We'll wait till after probably the next demo and we'll see if we can answer that question. But when you hear about electrolytes, smart water is one place you've heard of them. Where's another place you've heard of them? Gatorade, sure. Yeah. Gatorade would be another example. So in our next question here, this is on your Socrative app. Which substance conducts electricity when dissolved in water? Is it sucrose, which is sugar, sodium chloride, which is salt, both of these, or none of these? I'm going to get a couple beakers of water lined up, and we'll just check them really quick here now to make sure that they do not conduct electricity. And then go to my chemicals here, and we're going to put to the one that's on your right, we're going to put salt, and then the one that's on your left, we're going to put sugar. So salt's in this one, and I probably need spatula for this one here. There we go. Put sugar into this one, stir it up, get some of that stuff to dissolve, and then we will stir up some of the salt here and get this one to dissolve. All right, then we're going to go ahead and check to see what We voted. So get your answers locked in. We'll count down. 5, 4, 3, 2, 1. Looks like everybody thinks at least something is going to conduct. Majority agreeing on sodium chloride, or both of them. So we'll start here with the sodium chloride for the first one. And we see that the sodium chloride is an electrolyte. And the sucrose, this one here is not an electrolyte. Let's write these down. Once again, sodium chloride was an electrolyte. And then the sucrose here was a non-electrolyte. Okay, now your question then about smart water was again?
Why do they say that it enhances taste?
Enhances taste. Okay, now I've never had smart water before, but I can answer about Gatorade. First of all, when is the person going to ever consume Gatorade? What is it intended for?
When you sweat.
After you sweat. And that's because when you sweat, if you ever taste your sweat, how does it taste? Tastes salty. And so you're replacing your electrolytes because your body needs these electrolytes for all these electrical signals that are going through your body. The way you think, the way your muscles move, the way your heart beats. That's all. If you want to see what's happening, we always take an electrical picture of it, hook you up with the electrodes to the machine, and we get that. So all of those important functions of our body depend on electrical signals. So when you sweat and lose those electrolytes, you have to replace those electrolytes. Well, how many of you ever drank salt water? Okay, and how does it taste? Yeah, salty, right. So it doesn't taste very good. So if you want to enhance the taste to it, what you do is add a little bit of sugar to it, or add some flavor. So I don't know about smart water, but my guess would be is it's add something in to enhance the taste of it, because salt alone.
It still tastes like water.
Yeah, and I don't know, but at least in the Gatorade, it's added in. The other function that the Gatorade will do is the sugar in the Gatorade is that basically if you've been sweating, you've been working out, and if you're running a lot, the sugar will supply you with the energy. Okay? So, anybody else? Okay, next up, we got 3 of them here that we're going to look at. They are potassium nitrate, copper 2 sulfate, and ethanol. And I just hear the oh crap going on right now. It's like, yeah, we need to be able to write formulas for all of these. And those would be great things. These would be like great test questions right here. Let's write the formula for these things out. So let's start with the potassium nitrate. Potassium nitrate. Potassium would be K with a charge of 1 plus. Nitrate, this is a to memorize one, would be NO3 with a charge of 1 negative. You have a single positive and a single negative, what happens to them? They disappear, the charges, and we simply wind up with KNO3. For copper 2 sulfate, copper would have a charge of 2 plus, that's what the Roman numeral 2 stands for. Sulfate would be SO4 with a charge of 2 negative. So now we have a 2 negative and a 2 positive. I hear people, yeah, write down those ions from my note card, right? Okay, so 2 positive, 2 negative, what happens?
They disappear.
They disappear, and we wind up with CuSO4. Next we have ethanol. Ethanol would have how many carbons? 2. And all alcohols have OH. So this would be CH3, CH2, OH. So now, looking at these 3, I would like to figure out which of these substances would be classified as electrolytes. What do you think? How do you think they should be composed to be an electrolyte? And you could have 0 answers on this. You could have 1 correct one, 2, or 3. You can select 0, 1, 2, or 3 answers. So put in how many ever you think is correct. And now, based on what we've observed thus far, we should have a little better idea of what they would be. 5, 4, 3, 2, 1. Wow, 50-50 on that, huh? Well, let's just see now if that's the case, if we did learn something. Okay, so first one we're going to do here is which one? Potassium nitrate. All right, so the potassium nitrate, we'll go ahead and put in a small amount of potassium nitrate into here, and we'll stir it up and mix it to dissolve. And we'll see if we're right. All right, we are. Good. Good job. And next one, we're going to try the copper 2 sulfate. Copper 2 sulfate, I'm going to knock these down if I don't put these out of the way. So copper 2 sulfate, we'll take a small amount into the spatula here and put that in. And we'll mix that up. Now the copper 2 sulfate, you'll see has kind of a bluish color, and has a bluish color because most of the compounds of the transition elements, when we combine them with a negatively charged ion, will wind up having color imparted upon them. And so we check this one out, and we see that it too is an electrolyte. Next we try ethanol. And by the way, where do we find ethanol?
Rubbing alcohol.
Okay, rubbing alcohol is not ethanol.
Oh.
That's isopropyl alcohol. Where do we find ethanol? Gasoline's one place. Long before it was in gasoline, where else did we find it? Alcoholic beverages, sure. So this is the alcohol that you can drink. Now, don't ever try drinking it in our lab because we don't have 100% ethanol out there. We have denatured alcohol, and denatured alcohol means it's been made unfit for human consumption. And why in the heck would we want to do that?
So people don't come in here and drink it.
All right, we don't want you drinking in lab. Not because it isn't fun to do lab after you've had something to drink, but simply because one of the things that we do is that we highly tax alcohol. It's a sin tax. And so if you go out and buy alcohol at the liquor store, probably about somewhere between 50 to 80% of what you're paying on alcohol is actually taxes. And so that's why you can get like a whole gallon of ethanol like you put in your car. And if you get like E85, it might be $1 something a gallon. It's actually cheaper than putting in gasoline. But you try to buy a gallon of Everclear or whatever in the liquor store, it's probably I don't buy it, so I don't know. 50, 60, 80 bucks, I don't know. But it's very highly taxed. So, and if you do try drinking in the lab, you won't die in all likelihood. I can't promise you that you won't. But what I can promise you is you're going to get very severe diarrhea. And so I would suggest that you don't do it. And your gut's going to hurt for several days. So don't do it. All right. And we can see here that it is non-electrolyte. Non-electrolyte. Okay. So how come and why did we correctly guess these here? How did we get these right? What were we looking for? Metals. Okay. And why did we not guess that ethanol would be an electrolyte? Okay, it's a liquid, but what else? You said these had metals and these here does not, right? So it's the non-metals. And that's actually sort of it. It's not quite on track. What it is, though, is if we look at the kinds of compounds they are, we can talk about them either being ionic compounds or molecular compounds. And which ones were the ones that did conduct? They were the ionic ones. So we saw in there, we saw that the potassium nitrate was an electrolyte. We saw that the Copper 2 sulfate was an electrolyte, and we saw that the ethanol here was a non-electrolyte. And so again, it has a little bit more to do with the fact that it has a metal in there. What you're looking for is that it's an ionic compound. Okay, so in order for it to conduct electricity, what we say is that the solution must contain ions. And so this is key right here. It must be in solution, they must be ions, and so if they're in solution, that must mean that they are dissolved in water. Which then will take us to the next question on the Socrative app. Now don't answer this one quite yet because I'm going to demo this one. And this one here, I'm going to go ahead and take some water, and then I need to find some calcium carbonate. Now there's a couple different places I can find calcium carbonate. One of them is on my cart, if I can locate it. I'm looking for a box of chalk. I'm going to break off a small piece of chalk, and we're going to put that into the water. And then I'm going to take a spatula here, and I'm going to try to break this piece up and try to mix it around to get it to dissolve. Okay, so I took a piece of chalk, which again is calcium carbonate. I'm trying to get it all dissolved. Now what you're going to find out is that no matter how long that chalk stays in there, this piece of chalk will not dissolve into the water. Okay, so if it does not dissolve then, in light of that, the demo, would you predict that calcium carbonate is or is not an electrolyte? 5, 4, 3, 2, 1. Okay. And so we go ahead and check this out, and we see that this is not an electrolyte. And the reason why it's not an electrolyte is because it does not dissolve. If we go back to our definition, and we just circle this here, it has to be dissolved in water, and the ions have to be in solution. So if it is insoluble, no matter what we try to do, if it does not dissolve into water, it can never be an electrolyte. So coming back up here then, we would say that calcium carbonate is a non-electrolyte. And it's a non-electrolyte because it does not dissolve into water. Now, as far as its formula goes, what is the formula for calcium carbonate? CaCO3. That's because the charge on a calcium ion is 2 plus. Carbonate is CO3 with the charge of 2 minus. The 2 plus and the 2 negative wind up canceling each other out and leave us with CaCO3. So if you're making notes of it here, if you just write down non-electrolyte, it's not going to make much sense to you, so you might want to make a little note of yourself. It's because it does not dissolve. Abby?
But if you when you write chalk on the side, why do you wash it?
It's because the particles are so extremely tiny, they don't actually dissolve. It's just like, even if you write on a chalkboard, the way that you can get the chalk off the chalkboard is to just wipe it down with a wet towel. And so it's just like if you had dust on it. If you had like dust on your windows or something, dust on the sidewalk, you can just wash that stuff off. Dust and dirt, that does not dissolve in water either. But you can wash it off because the particles are so tiny. Well, mainly because they're just so tiny. Because once you put it on there, just think about if you write it on a chalkboard or something, it's such a tiny layer that flushing with water is going to take it and remove it real easily. Yes?
Since calcium is a metal,
Yes.
doesn't that work? So it just doesn't follow the ionic rule.
Well, it does follow the ionic rule, but in order to get those ions in solution, you actually have to make it dissolve. So not all ionic compounds are soluble. So that's why when we talk about it, it's not just the fact that it's an ionic compound. It has to be an ionic compound that dissolves in water. So if it doesn't dissolve in water, even if it's ionic, it's still not going to be an electrolyte because it has to meet two criteria. You have to have ions in solution, and it has to dissolve when it does so. Okay, any others? All right, then the next ones that we're going to look at 4 of them coming up next. The next 4 are going to be ammonia, hydrochloric acid, acetic acid, and the last one here, sodium hydroxide. So then we got to write out some formulas. Now to write out the formulas, we'll start with ammonia. Now this is ammonia, not the ammonium ion. Ammonia is one that you are to memorize, just like you memorize that water is H2O. We don't call it dihydrogen monoxide. Ammonia is NH3. If you think of NH4, you're thinking of the ammonium ion, which is NH4 with a charge of 1+. This is ammonia, which is NH3. Hydrochloric acid is HCl. Acetic acid is H. Remember now this is an IC acid suffix, so it's derived from the acetate ion. So it'll be H, C2, H3, O2. And I hope we can all get the last one. Sodium hydroxide would be NaOH. Now these last 4 we're going to look at separately, kind of as rules that are different than the rules from before. Because up to this point, if you saw an ionic compound that dissolved in water, that meant it was electrolyte. If it was a molecular compound that dissolved in water, it would be a non-electrolyte. So whatever rules we learned, keep them in mind only for the ones that are up above. Is again, have you guess, and I think this is the last of the Socratic questions, which of the following substances would be classified as electrolytes? And while you're doing that, I'm going to get these lined up here to test. Oh, and by the way, chalk. Our lab this week that we'll be doing is one where we are working with antacids. And I don't know if any of you have done the pre-lab quiz yet, but the antacid found in the antacids we'll be looking at is calcium carbonate. And so we'll be working with Tums, I believe. If you've ever taken an antacid before and said it has kind of a chalky taste, there's a reason for it. It's because it's the same stuff found in chalk. So if you happen to have a teacher in the house that still uses chalkboards, and you have an upset stomach and you don't have any Tums lying around, just chew on a chunk of chalk and that'll do it for you. And if you don't have this, how many did the egg lab here a week ago? Anybody do that egg lab? Okay, just a couple of you there. All right. There's again always the ones that don't need it, right? Okay, so the egg lab, the calcium carbonate, the eggshell is actually made out of calcium carbonate as well. So if you have an upset stomach, you could always peel a hard-boiled egg and take that eggshell and eat the eggshell, and that will neutralize acid in your stomach. And if you don't have access to any of those and happen to have a marble statue, marble is made out of calcium carbonate. You can chunk a chip off a marble statue and munch on that, and it'll do the same thing for you. Chemistry, it works all the time. So we'll check it out here. Here we go. We have ammonia as our first one. And so we're going to try ammonia right here. And now ammonia has kind of a strong smell, so I try to keep this as an arm's length, just so I don't have this up on my nose. This here is the water. I'll go ahead and add the ammonia to it. Cap back on here, and we'll test it really quick. And many of you are saying that it would be an electrolyte, And we see that it is, but what's one big difference that we're noticing? It's dim. And so here's where we're going to have to start using some, I think they're called adjectives. I'm not not an English major. Yeah, they're called adjectives. I know that much. All right, we're going to start using some adjectives. The adjective we're going to use here, we're still going to call it an electrolyte, but the adjective we're going to use is we're going to call it a weak electrolyte. Which means we should go back and put some adjectives in front of the other electrolytes we looked before. And the term we'll use there is a strong electrolyte. So for all of the electrolytes that we did before, go back and fix them and add in the word strong in front of them. And we say that a strong electrolyte is one that is strongly conducting, and a weak electrolyte is one that is weakly conducting when dissolved in water. So that there was the ammonia. Next up here, we are going to have the hydrochloric acid. And so again, we'll check our water here really quick. We see that the water does not conduct. And we have the HCl. And I keep this at an arm's length because you might see right now that there's kind of a gas or some fumes that this is giving off. I don't want to inhale those. So we'll go ahead and test this out, and we see that HCl is a strong electrolyte. And then we'll go on to the acetic acid. Now the acetic acid is one that I like to look at here because I'm going to walk around with this one. As I walk around it, I think you should identify the smell of acetic acid. This here is 100% acetic acid. And if you're smelling it, what are you smelling?
Eggs.
Oh, you're not smelling eggs. Sulfur. What the heck is this? Oh, we don't want to get our nose over there.
Vinegar.
Vinegar. There you go. Now you're gonna start. You don't smell it yet? Yeah, you got it now. You got the vinegar. So it usually doesn't take too long for me to walk around in here, and you wind up smelling the vinegary smell, and that's because acetic acid is the acid found in vinegar. Now the difference is that vinegar is about 5% acetic acid. This stuff here is 100% acetic acid, and that's why it smells so strong. That's why you can walk through here and know that you're going to wind up smelling it eventually. Okay? So what I'm going to do with this one though is I'm going to pour some acetic acid into this beaker, and then I'm going to take some water and we'll test the water. We'll see the water by itself doesn't conduct. We take the acetic acid, we see it by itself does not conduct. Here's the water, here's the acetic acid, and if I pour the acetic acid into the water, we see that we wind up with a conducting solution. And we wind up classifying this one as a weak electrolyte. This one here is a weak electrolyte. And then we're going to wind up with the last one here, which is sodium hydroxide. And the sodium hydroxide comes as a solid. And we'll go ahead and place a small amount of the sodium hydroxide into water. We'll check the water here really quick to make sure that it's not conducting. We'll go ahead and take a few flakes of the sodium hydroxide out of this one and put in. Cover this up. Mix it up a bit. And we see that it is a strong electrolyte. Okay, now, where all of that stuff comes into play is right here. There's a reason why we talk about electrolytes. We want to know the strength of those electrolytes. And there's a reason why I said that we're going to consider these separately than the rest. Because, first of all, we would have not predicted. There's a reason why many of us here did not correctly select that ammonia was going to be an electrolyte, or that hydrochloric acid or acetic acid would, because all of those are molecular compounds. They're all molecular compounds. However, here's how we define an acid. We define an acid as a substance that produces H3O positive when dissolved in water. And we define a base as a substance that produces hydroxide ions when dissolved in water. And so what this means is that even though we have things that aren't ionic to begin with, what happens is when we place these things into water, they actually make ions. So even molecular compounds can react with water to make ions. Now, we did not look at this one earlier this semester. We did not give it a name, but it does have a name. This one here is called a hydronium ion. And the reason why we didn't name this earlier this semester is because hydronium ions are not found in compounds. So we don't have things like hydronium chloride, hydronium nitrate, or hydronium sulfate. We don't find them in compounds. The only place we find them is in aqueous solutions of acids. So once I pour an acid into water, then there's a reaction that takes place that makes those ions. But they're only present when we have an aqueous solution of those materials. And so we wind up using the terms like this. We use the terms strong acid, strong base, weak acid, and weak base. And when we use the terms like this, strong and weak, here's what that means. If we have an acid that is also a strong electrolyte, then we call it a strong acid. If we have a base that is also a strong electrolyte, we call that a strong base. If we have an acid that is also a weak electrolyte, we call it a weak acid. And if we have a base that is also a weak electrolyte, we call it a weak base. So these terms here refer to whether they are strong or weak electrolytes. So then we go back to the acids and bases we looked at here today. And we're going to start with ammonia. Ammonia. We're going to write out a very quick reaction for the ammonia. And here's how the ammonia looks. What happens is that we start with ammonia, which is a molecular compound. We react it with water, and when we do that, we wind up producing ammonium ions and hydroxide ions. And because it produces hydroxide ions when we put it in the water, that must mean that we classify ammonia as a what? It's a base. And specifically, what type of base? Well, we come back here and we see it was a weak electrolyte, so that must mean it is a weak base. Well, then we look at hydrochloric acid. Well, just from its name alone, hydrochloric acid must be classified as an acid. And if it's an acid, that means when it reacts with water, it's going to make which ions? Well, all acids will produce hydronium ions when dissolved in water. And then what we have left over is chloride ions. Well, because it produces hydronium ions, it's classified as an acid. And specifically, what type of acid? It's going to be a strong acid. We know it's a strong acid because back here we saw it was a strong electrolyte. Then for the next one, we did acetic acid. So acetic acid is also a molecular compound. But when we put it into water, all acids will form which ion? Again, it's going to be the hydronium ion, and what's going to be left over is the acetate ion. So just its name alone tells us it's an acid. If we go back, we see it's what type of acid? It's going to be a weak acid because it was a weak electrolyte. So we label this as a weak acid. And then if we look at our very last one that we did, it was sodium hydroxide. Now we don't need to write out a reaction of sodium hydroxide with water because sodium hydroxide is already an ionic compound. So what happens is that when we put it into water, it'll simply separate into its constituent ions, and it'll form sodium ions and hydroxide ions. And because it forms hydroxide ions, that must mean it's classified as a base, and the type of base is going to be a strong base, because if we go back here, we see that it was a strong electrolyte. So these are how we wind up applying those terms. It has nothing to do with their concentrations. And so now, the important thing to know about this is this. I have a story, and I won't have time for today, so we'll start with a story on Thursday. But I do want to tell you this much, though, before we leave. And this much is this. Even though acetic acid is a weak acid, right here, this is a weak acid. Okay, the term strong and weak applies to whether they are strong or weak electrolytes. It has nothing to do with how concentrated or how dilute this stuff is. And the story that I will tell you on Monday has to do with getting myself some terrible skin burns from this stuff in the past. Okay, and so I treated this chemical very poorly because I did not have the respect for it I should have had. I didn't know that I was supposed to have respect for it. I was a student. But when we talk about the properties of acid and bases, one of these properties right here is they cause skin burns when concentrated. Doesn't matter whether it's a weak acid, a strong acid, weak base, strong base, whatever. As long as it's concentrated, it can cause skin burns. And I've been burned actually quite severely by this. Treating it poorly because this is the same acid found in vinegar. And so you think vinegar, yeah, this can't burn you, but it does when it's concentrated. So anyhow, that's it here for today.